Alright, hey everybody. Sorry for a little bit of delay with getting these physics videos out. I'll try to do a couple a week at least, and I'll keep you updated as we go along. I got a little writing tablet here. I'm kind of useless with it, but I don't know, we'll see how it goes. I'm about as good with it as I am with the smartboard. Anyways, just to review, we started Unit 3 before the break. It was about uniform circular motion, meaning something moving in a circle at a constant velocity, right? And so if I'm going to move around this sweet circle and my velocity is some constant number, what's going to happen? Now, one of the things with Newton's laws, I think it's Newton's first law, says if I go in a straight line, I want to keep going in a straight line. So in order for me to stay around this circle, something has to pull me, some sort of force has to pull me so that I won't go in that straight line, even if my velocity is constant. And we decided that there is some sort of force, and it is always towards the center of that circle. And that force is equal to a mass times some centripetal acceleration. And we also figured out that that centripetal acceleration has a value of your velocity squared divided by your radius. And to take that even a step further, if you replace v with 2 pi r over t, which is the distance around the circle divided by the time it takes to go around the circle, the period, then we got a couple of other formulas. I think it was 4 pi squared r over t squared, and we also got 4 pi squared r times the frequency squared as well, because frequency is equal to 1 over the period. Alright, so I'm going to add a new page here. And what I wanted to do was just kind of go over all of the topics with a few questions I'm going to take from the textbook. So the first question I want to take is this one. Have a look there. It's a hard question, I think. It's from page 124, and it's number 6. It says an air puck with a mass of 0.26 kilograms is tied to a string. It moves at a constant speed on this circle. The string is, there's a weight dangling from the string through the middle of the table, so we'll kind of treat that like a pulley. And there's no friction, so it's like on an air hockey table or something. So we'll do that question and see if we can review that, kind of review what we've been doing so far. So right, question 6 there. Let's do a free body diagram on our puck here, maybe looking down at it from the top. So there's the puck. We're looking down. It's attached to this string that's going to go through the table, and there is only one force on this thing, okay? And that force is some sort of centripetal force. It's a force of tension. Okay, the string has to pull on the rope. So if I do my Newton's second law, which is take all your forces, add them up, let them equal the mass times the acceleration, I will get that the force of tension will equal the mass times the acceleration, which is ACP. Now this question is asking me to find the speed of the puck so that it just, so everything is kind of in equilibrium. So how am I going to find, well, I'll say that the force of tension is equal to the mass, which I know, and the acceleration is just v squared over r, like that. Okay, so I'm looking for v. I know r. It tells me that r is equal to 1.2 meters. It also tells me the mass of the puck. It's equal to 0.68 kilograms. I just don't know the tension in the rope. But if I look at it from another view, so this was my top view. If I look at it from the side view, and kind of think about it like a pulley. So there's my rope, it's bent around. There's some sort of mass on here, right? This thing is in perfect equilibrium as well. So the tension in the rope, if I just look at the free body diagram of this thing, right, I will see that there is some sort of tension pulling on it. And then this is the mass times gravity. And those two things will have to balance in it, because it says the system is in equilibrium. So I can actually find the tension I need to solve for my velocity from the free body diagram of this mass that's dangling. And sorry, the puck is not 0.68 kilograms. The puck is 0.26 kilograms. Let me just erase this if I can. There we go. 0.26. And this mass here, what happened to my thick pen? Oh my goodness, this thing is tricky. Okay, equals 0.68 kilograms. I don't know what I did. Anyways, all right, so what does the tension equal in this drawing? The force of tension will have to equal the mass of that weight times gravity. Okay, so if I just scroll down here, I can then say, if I take this equation here, combine it with this equation here, then what's going to happen is I am going to get that the mass of the puck times the velocity squared over r will equal the mass of the weight, I guess, times the gravity. And then I can solve for v squared. So v squared is going to equal the mass of the weight times gravity. I'm going to bring my r up into here like that. And I'm going to divide that by the mass of my puck. So I have a nice simple formula for velocity squared, and I could just figure out on my calculator what those numbers equal. Let me just punch those in. I probably should have done this ahead of time, but 0.68 times 9.8 times the radius, which is 1.2 meters. I'll divide that by the mass of the puck, which is 0.26 kilograms. Hit equals, and then square root that answer. And the answer that comes up on my calculator is 5.5 meters per second. So there you go. If I look at that question one more time, if I can spin this puck 5.5 meters per second, I don't know how you're going to do that, right? Just by giving it a push or something. I don't know what gives this thing its initial speed. But if I can spin at 5.5 meters per second, this mass will just dangle perfectly in equilibrium. If I go any slower than that, then this mass will slowly fall because there's not enough tension in this rope. And if I go any faster, this mass will force out and create a bigger radius and try to pull the mass up. It's kind of an interesting question that covers a lot of the topics we talked about. So try that one on your own, maybe without watching me do it, and then see if you can do it. Also, maybe try from this page. I don't see too many good questions, but number 4 is is a decent question, and so is number 2. So maybe try those on your own as well. Again, we're just going to have a short quiz on this stuff as kind of like a unit test. Okay, so stay tuned at the end of this week. I'll give you more details about that. The other question I wanted to try with you guys is on page 130, and it is question number 7, which kind of covers a lot of the topics that we did before the break as well. It says there's an astronaut with a mass of 65 kilograms, and they're in a rotating space station. Remember we talked that when we talked about frames of reference, as long as the astronaut can't see out the windows to know that they're spinning, basically what they get is a normal force if they sit around the outside of a ring and they're in like dead outer space. There's nothing that provides gravity. If you're in some sort of spinning object, then you will gain a normal force against the outside edge of that thing. We call that centrifugal force. It's kind of a fake force that you experience when you're inside something that's going in a uniform circular motion because of the centripetal acceleration. So it says she stands on a scale and reads 140 newtons. So that's an Earth scale. And Earth scales are designed to take your mass and times by 9.8 to give you newtons. So we'll have to use that information as well to get the answers that we're looking for, which is what's the acceleration in the spaceship when you drop stuff near the floor. So basically, what does gravity feel like in there compared to Earth's, which is 9.8 meters per second squared. Calculate how fast the thing will have to rotate to maintain that gravitational like force, and then calculate the period of the space station. So let's try that one as well. If you want, it's a good time to pause it, try it on your own, see if you can do it, see if you can remember all the stuff that we talked about. If not, just watch along. Okay, so new page. This is question number 7 on page 130. I'm going to put this person on a spaceship like this, just along the outside so we can see that it doesn't matter where this person is in the spaceship. We're in deep space. There's no bodies of mass that are going to offer up any gravity to anybody. So we got to make our own by spinning this whole thing constantly. Remember that clip from 2001, A Space Odyssey, where the people are running along there. Just make sure there's no windows in your spaceship, or people will get very ill very quickly because your brain does not like to think it's spinning. Okay, so what's the free body diagram on this person? We can look at it from 2 perspectives. We can look at it from this person's perspective inside the spaceship, or we can look at it from the perspective of someone watching it happen outside of the spaceship. Either way, it's all the same math. If I look at it from the person's perspective inside the space station, and I just want to do a free body diagram on this girl, then what I'll have is a normal force on her. Okay. We've already decided that the book has decided for us that that's 540 newtons. Okay. Your normal force is how much you weigh on a scale. And the only other force on this person is this centrifugal force, which is this fake force that has to balance this normal force. And if it doesn't, then it's saying that if these 2 forces don't balance, then this girl's either going to fall through the ground, fall through the spaceship, which can't happen, right? She's pushed along the edge, or she's going to float off the ground in the spaceship. So these 2 forces have to balance. There's no acceleration on her from her perspective, right? She's just standing there. So that's what's weird about these frames of reference question. If I look at it from the perspective of her, let me grab a different color here. I don't know what color this is, but if I look at this from the perspective of someone outside of the spaceship, then she still has a normal force on her, but that's all she has, because she actually has an acceleration of v squared over r. Okay, the math is still going to work out because this centrifugal force always equals the centripetal acceleration anyways. But I'm going to do it from her point of view just for now. So I will say that the normal force has to equal the centrifugal force, which equals her mass times the centrifugal acceleration, which is the exact same value in the opposite direction of centripetal acceleration. So it's going to be her mass times v squared over r. But I don't even need to go that far yet. For this part here, the part A in the question says, at what acceleration do objects fall when dropped near the floor? So I'm going to take this part here and say that 540 newtons equals her mass, which is 65 kilograms, times the acceleration. So that way I could find the acceleration that she's experiencing on this ship. Easy enough to do. 540 divided by 65, it equals, it's 8.3 meters per second squared. 8.3 meters per second squared. Okay, so a little bit less than Earth's gravity. If I want to find the speed, that's easy to do as well. I'll just take this one here. So this is part A. Part B says that her speed, again, is just the 540 Newton normal force. That's what's read on the scale. Is going to equal mass times velocity squared over the radius. It says the radius in the question is 150 meters. It says the mass of this woman is 65 kilograms, and so we can solve for velocity. I'm just going to bring the r up and the m down and square root it. Skip some steps for you guys. I know you like that. Divide by 65 times by 150 meters and square root it. So the speed of this spaceship, my pen go there, I get 35.3 meters per second. Okay, so pretty fast. It's like 100 kilometers an hour, but you never know it as long as they don't put windows in there. All you know is you're kind of pinned to the ground a little bit, which is good when you're out in space. You need that. Your body is designed to, your heart and your muscles and everything are designed to kind of live with this force on you all the time. And if you don't put that force in place, it weakens your body a lot. Calculate the period of rotation of the space station. Well, the period is related to the velocity through this formula here, 2 pi times r times the period. So you could figure that out pretty easily. How long does it take for this thing to go around once? It will be 2 times pi times the radius, which is 150. And that will be divided by the speed we found, 35.3 meters per second. So it takes around 27 seconds, or 26.7 seconds to go around once. Okay, so that's the two questions I wanted to just try to get you caught up and see what we've been doing, or see what we did before the break. If you want to try any other questions, try 8. 8 is a pretty good question. And number 6 as well. So see if you can do those. If you have any concerns, email me them. I can also take them up on this little notepad thing too, so it shouldn't be too hard to do that. Okay, so stay tuned for some more. We're going to learn about gravity next, where gravity comes from with regard to mass, and we'll learn about satellite orbits, and then we'll wrap the unit up with that stuff. Okay, see you soon.